Okay, I guess it's time. So let's get started. Um, First of all, thank you very much for coming to my talk. I have to warn you, I'm a little sick today this morning. I developed a cough, so I'm going to be coughing a lot during the conversation. It's mainly going to be coughing. But please excuse me if I do that. So my name is Yash Ranadive. I work at Lookout Mobile Security. We're a security company. And today I'm going to be talking about Storm as an ETL engine into Hadoop. Before I start, I just wanted to get a feeling, rough show of hands. How many people here have heard of Storm? Wow, that's pretty much everyone. That's great. How many people here are using Storm in production? Few hands. That's great. That's great. So that's good. I mean, we're all here to learn, so that's good. So just wanted to get a feeling of it. So before I start, tell you a little bit about myself. I'm a data engineer at Lookout Mobile Security. I've been there about 2 years, and my main job is to basically support the analytics infrastructure pipeline and ingesting data into Hadoop. And if you're interested, that's my blog. I like to blog things about ETL. So today's agenda is, just wanted to lay the groundwork of when would you want to use Storm. There are a lot of big data technologies out there, each one with its own specialty, and I kind of wanted to compare that with some of the other things and to see when are some of the use cases when you would like to use Storm. I'm not gonna go too much deep into how Storm works or the architecture of Storm itself, but if you have any questions, please feel free to ask me afterwards. And I'm going to talk about some architecture alternatives that you can do with Storm. These are just some. There's a whole bunch. You can do whatever you like. And I'm going to go more about the operational stuff. And finally, we'll be open for questions. So Lookout is a mobile security company. We have an iPhone and Android app. And we have other features within our app as well. One of the biggest features is the antivirus for Android. We also have features such as missing device, so it helps you locate your device if you've ever lost it. We also do contacts, backups. We have over 60 million registered users, so that kind of gives you an idea of the kind of data we are looking at. A lot of it is data of devices connecting to our servers and relaying information. So again, a quick show of hands. How many people in this room identified themselves as ETL developers or ever had a job as an ETL developer? Great, that's a lot, right? And I've been doing ETL for the last 6 years, and the traditional definition of ETL, plainly put, is just moving and transformation of data so that we can store it and analyze it, right? You're gonna have various ways of doing it, but that's sort of like the main traditional definition. But these days, it's changing, right? It's no longer just doing that. We're no longer stuck in the database world where we have one SQL Server Oracle database. We're getting large amounts of information, and we're at the Hadoop conference. Hadoop is becoming very popular. And it's not just that. Because the way we have changed the way we are ingesting data, we're ingesting not just large amounts, but it's large amounts of event data. And it's not relational database, or you're not taking a large dump from a relational database into Hadoop. We're investing a large amount of event data into our systems. So as a ETL developer, when you're building out your ETL pipeline, the main question you want to answer is how can I build a generic framework so that I can take data within these pipelines and land them into Hadoop or any sort of analytic system it is. And if you ask any business person that you work with, and you ask them a question, okay, how soon do you want that data in there? They're going to tell you as soon as possible, real time. I want sub-second latency for a daily report, right? So, so one of the things that as an ETL developer you want to do is make that data available to them as fast as possible, and do anything in your power to do that. And then from then on, people can do whatever they want with that data. So. Interesting. So the problem is kind of what do you use in this kind of gray box, right? And it all depends on a couple of things. I'm just listing very few things, right? What are your latency requirements, for example? I'm grouping the analytics latencies into this very sort of high level criteria. If you have the batch reports, which happen daily on an hourly basis, and so on and so forth, you could have some more frequent batching where you can potentially run like a batch level job, such as a Hadoop MapReduce job, every 10 to 15 minutes if it finishes early. And then you have the near real time, which is sub-second under a minute latency, and then you have the sub-second latency as well, which is that you would possibly want information for, right? It's not, when you're talking about sub-second latency, it's not a lot of business users who want it, but there's definitely the operational users or people who are looking at the health of the pipeline who want to know that information. It also depends on your complexity of reports, right? If you're looking at something on a more throughput level, wherein you're just doing counts of data, which is much easier than versus doing a join with a complex table, or if you have a users table or a cohorts table that you're keeping track of and want to join to that large table, you have more complexity. So you can kind of group them in that. So on a very high level basis, we're doing two distinct things in there, right? Like I said earlier, we're getting data off of message buses, and we're getting a lot of event data, and more likely than not that it's going to come through like an ActiveMQ or a Kafka, and you want to have something to offload that data and then put that data into your analytics system. So you're doing two distinct things. The first thing is offloading of the data, and then the processing of the data afterwards. So these are just some of the options that you have available right now, right, for offloading and processing of the data. You might want to go choose in a very batch format where you offload the data, the messages off of Kafka into Hdfs using something like Camus, and then process writing your own MapReduce statements, or using something like a Scalding, which is a framework. Or you can go with something which is Storm, which does the real-time offloading and the processing of the data. So we at Lookout use Storm for some of our pipelines for real-time analytics, and mainly pipelines which involve a combination of views into them. So today I'm going to talk about how we ended up solving two problems. One of them is called user gratifications, and the other is device connections. These are names of the pipelines. To give a little background, at the analytics team, we are always looking at how users are interacting with our products, and how we can take these users and have them, split them up into cohorts, as we call them, so that we can track better on how people are using our product. So user gratification is an internal term that we use, and gratification, simply put, is just an event that adds value to a user. So in the context of our application, it's stuff such as if a user successfully locates their phone, or if they scream their phone, or if there's a wipe event that happens on the phone. So something which pretty much helps our user in any way we want to track. And we want to make sure that we are tracking it all the time, and we want to make sure that there's no downtime in that tracking. So from the analytics perspective, those were some of the goals. So the events were coming to us via protobuf format. Protobuf is a data encoding scheme, I guess, if I said that right. But basically, it's binary data that's coming off of Kafka, and we wanted to monitor the throughput of the data, make sure that we're not, if nothing bad is happening in our systems, and we catch it if something happens. And also, we wanted to do a lot of high-level reports, which were highly complex, which we were joining to our cohorts table, for example. It's kind of like a group of users table. And we wanted to create very sort of granular reports, what the users can slice and dice. So long story short, that's kind of what the requirement for the data pipeline was. This is what we ended up doing. We built a Storm topology. And this diagram is a little heavy on the content. But again, not going too much deep into the way Storm topologies work. Storm topologies basically consists of bolts, or spouts, which is your data entry point into the topology. Then you have the bolt, which then processes this data, and then you have multiple bolts which can be lined one after the other. In this case, we use the Kafka spout. It's freely available, open sourced. I think somebody in Hortonworks wrote it, and actually, I take that back. Not somebody in Hortonworks. That might be that gentleman sitting there who wrote Storm HDFS bolt. But anyways, so we use a Kafka spout, and then we use a bolt to deserialize the protobuf, which is taking that binary information and projecting it into columns. And we need these columns for our reports downstream. And then we use the Storm HDFS bolt, which then takes the information and then puts it onto a landing directory within the Hadoop. Right, and this landing directory is a temporary directory where it streams the information and syncs the information to the file system. And within a given amount of time, or within, let's say, you can say for every 5,000 messages, or every 5 minutes or 10 minutes, you can then finalize that file, and then it rotates into the Hive directory. Or in other words, it's basically a Hive table. Hive external table, which is backed by a Hive folder in HDFS, right? So that's kind of what we built, and there are a couple of tuning options that are available in here within the Storm HDFS bolt, and which are good and bad. Good in the sense that you get more granular detail of how you're operating the landing of the data, because how you land the data determines how fresh your data is in your Hive table. So some of the tuning options are changing the hsync count, which is the number of counts it takes to then flush the data into HDFS. And then, so the other thing you can do is change the parallelism of the bolt itself. So the Storm HDFS bolt, which is writing the data to HDFS, you can change and have it run on multiple worker nodes, or have it run in parallel so that you can get higher throughput. So these tuning options you are gonna run into when you deal with changing throughputs. So if your pipeline is ingesting 100 messages a second, and next week you add more servers and now it's 2,000 messages a second, those are some of the things that you'd have to do. And this thing I haven't looked into much, but it's possible that you can have more of a Storm HDFS time-based sync policy, wherein your records would be synced into HDFS based on a time period. And I'll cover in the future why that would be interesting. But for now, so those are some of the tuning options you looked at it. The good thing about this pipeline for us was, we were getting data which was ingested as binary protobuf format, which in itself, looking at Kafka, would be really impossible for someone to read. So a good thing was we had that plain text converted into, protobuf converted into a plain text format just by tailing a file. We got that. The other thing we did was we got let me get some water. The other good thing about this was we used Storm to publish metrics to statsd. And statsd is basically a event, or let's say statistic aggregation server. And then we viewed the data via graphite. And this helped us understanding a better, deeper knowledge of the throughput of the data. And again, the data available is for downstream analysis. If you notice, it says insert diagram here. I think I submitted a different copy, and this is a different one. So I apologize for that. But you will see the diagram that's in here later down the line. Okay, so moving forward. This, within Storm, there are two APIs. One is the Storm, and another one is called Trident. Trident allows you to do exactly one semantics, which allowed you to make sure that you're processing one message only once. So this, while it's not a challenge, if you are not careful, you can actually just build a regular topology, and then you can have possible duplicates within your data, which is landing on Hdfs. You can cure that by deduplicating further down the stream, but that's one thing that was kind of a little bit of a challenge for us. The other thing was the Storm Hdfs bold particularly has limitations, and Taylor, let me know if this is wrong, because I wasn't able to find a solution for this. But when, going back to the pipeline, if you had this pipeline running and it's putting data into the landing directory, if, let's say, you were to kill the pipeline in Storm, the way you would do that is, the way Storm does that, it sends pretty much a kill -9 to the worker node that's running the JVM, that's running your thread, which is shoving data into Hdfs. It would actually send a kill -9, which means that it would just abruptly end writing data into the landing directory. And then you would have to then manually rotate that file into the Hive folder. So that was another, that was a limitation. The other limitation we thought was sort of, no, we didn't find a great way to sort of build a set of parameters, or have a set of parameters which would work for 2 messages a second versus 2 million messages a second, right? So some of the things that you're in here that you can tune, such as the count of the number of messages, for fsync sort of limited our ability to have varied levels of throughputs. So in a situation where we had bursty traffic, for example, this is actually actual production data. We had a topology which was only processing not very many messages per second, and then there was a, I don't know what exactly happened upstream, but we started processing a whole bunch of records. And this was not an error. There was something generally happened upstream which caused that. All of a sudden, we started noticing that there was a lot of lag in our topology. That is, the topology wasn't processing events as fast as possible. And the reason why we were doing that is because we had set the count of the sync within Hadoop way too low. And so basically, it was getting 3,000 messages, and it was trying to sync every second or half a second or so on and so forth. So that's somewhat of a limitation. So the parameters that you would end up putting in your topology would be dependent on your throughput. And there might be better solutions to this. I'm interested to see what Taylor has to say. The other topology that we created was to ingest device connections. And these are a way for us to determine if our users are using our application, to see if they're still alive or dead. So we had a topology where we were getting data into JSON format, and we had to do a join to the table, so on and so forth. So pretty similar to the last report. I'm not going to go too much into the details of this particular one, but it's just another way of doing ETL into Hadoop via Storm. So for this particular one, what we did was we landed the data on HBase first. And we had a Storm topology which would write to a table in HBase. And that table had a TTL, or time to live, of 3 days. So the data in that table would be for the last 3 days worth of data. And then we had a Hive table which was also accessing that table with the HBase SERDI. So the Hive also had a view of that table. And what was happening in real time was that we were taking data off of the bus, extracting data or projecting columns from the JSON data, and then moving that data into HBase. And so we had a copy in HBase. And then we had a batch job on a daily basis that would then load that HBase data into a Hive table. And this Hive table had the history of pretty much all the days. So that's one other way that we found we could do it. So the good thing about this is we were, sorry, we're definitely able to query Hive sort of real time, in the sense that the data landed in HBase in real time, but if you wanted to access it, you could run a Hive query, which would then run a MapReduce job off of a HBase table. Long way of doing it. But the second point, we thought that this was not too much of an issue now because I think we changed some of our jars, but we saw better stability with this one than the other method. But that kind of has changed recently. I'm not quite sure what, but something within our Maven got in our pom.xml got a newer jar, and I think that issue has sort of resolved itself in a weird way. I don't know. So that's sort of how we got the data in the system, right? Now, how about analytics across the system? So with this sort of architecture, we get 3 points where we can actually run our analytics queries. Each point is sort of limited in its scope of what it can run and what analysis can do. Going back to StatsD, StatsD is an aggregation framework which is great for doing counts. So if you're counting the number of events which are coming through into your system and you want to make sure that you always have a visual monitor of that, we actually have that. We have a visual monitor of the number of gratifications which we monitor because it's a very important metric for us and for the analytics team. StatsD is great for that, and you can visualize the data via Graphite. You can, once the data is in Hive, you can do a lot of ad hoc queries or whatever you want to do, or slice or dice or whatever. And then Tableau is great. People have been using it for a while, and we use Tableau for slicing and dicing and some of the complex reporting which gets developed based on our stream data. So, okay, now is the operational stuff. Something, I'm going to talk briefly about how we went ahead and did some of the kind of boring details for the operational side of things. Topology deployment was really sort of simple in the way. We use Gerrit for code review. So if somebody wanted to push a change to the topology or add a new topology, they would submit their code to code review. And once it got +2 there, we would use Jenkins to build the Storm jar, which would then get pushed to Artifactory. And then we would move these jars to a common Storm gateway server, which we use to kick off Storm jobs. And so let's say if we had a topology that's already running and we wanted to push a change to it, we would then, sorry, it should be the other way around. It should start the new one and then kill the previous. I got the order messed up. Sorry about that. So you would start a new topology so that you don't have any downtime and then bring down the other topology. So that's pretty standard. I think it's straightforward. Configuration management is simple as well. We kind of abstracted out all the tuning places that you can tune your Storm topology into so that it could be configured via an external place. In this case, we just passed the configuration parameters to Storm via the command line. So we use the Java options class to sort of come up, do that level of parsing. So that is stuff like statsd host and how often you want the sync to happen and parallelism. You can also put bolt level parallelism in it. So if you were expecting a lot more data for one day, for example, you can also do that over there. So that's pretty standard straight configuration management. This is an interesting one. So you build a Storm topology, and that's actually shoving data into Hdfs. One of the things that you want to know is that your topology is processing data as fast as it can, or in other words, it's keeping up with the data that it's getting via the message bus. Now, this is really important because you might have a situation where something happens and then you're not actually getting the throughput that you want. And there's a lot of data, there's a lot of back pressure that gets collected into Kafka. So we use a tool called Datadog to monitor this. But basically what happens is Kafka has an idea of a consumer group. And basically a consumer group in Kafka is basically saying, hey, I'm a consumer and I have multiple consumers which are going to try to take data from a Kafka from a Kafka topic. And what I would do is then put my offsets in a Zookeeper directory. And we have a tool which then looks at the offsets and looks at the latest offset within Kafka and then does a diff of that to find the number of messages that are still in Kafka that we have not processed yet. So this is a really important thing, I think, to measure for any storm topology, is the lag of the consumer. And then, yeah, we're doing that in Datadog. And again, just regular metrics like throughput, and so we are doing using statsd and graphite. The other thing that I wanted to make sure was, since this was such an important pipeline, is that we make sure that it's always available. So we so we have a job, a Ruby script rather, which hits Storm's Thrift API, and the API basically gives you access to pretty much any of the Storm minute details, such as the number of messages transferred within a bolt or transferred within a spout, so on and so forth. So we use the Storm Thrift API to see if a topology is active, and we only alert on high-level metrics. What I'm trying to say is that, let's say if you have a bolt which is running and it's trying to get message, a spout rather, trying to get message off of Kafka. Now there might be network errors which is preventing it from doing it for a short amount of time. That will cause a failure within the bolt, and the Thrift API will show, okay, you know what, I'm having failures. But that's just way too noisy for us, and so we just capture it only on the high-level metrics to prevent alert fatigue. Otherwise, we would get alerted way too often. And the environment, we're a small cluster, not big at all, and that's pretty much it. So, you know, I think the end of the lessons learned sort of in here is that it's important to understand when you would want to use Storm versus some of the other batching technologies that are out there. Batching is definitely more it gives you much more power. That, for example, if you want to do a join on a 10 terabyte table, or something that does not fit in memory, batching just gives you much more power in that sense. But there are some use cases where Storm is great, and it actually has a niche place in between the batching and between the batching environment and the super real-time processing that people use for more operational things such as sending emails, so on and so forth. So there's this niche sliver where the data warehousing topologies fit in. I hope I did an okay job in explaining that. Again, the HBase one, you can try multiple methods. Both of them are more or less same. There might be a few things that I'm missing here, but cool, that's pretty much it. I think I have 11 minutes for questions, 12 minutes rather. So I'm ready to take questions if anybody has any. Sure. Yeah, so the question the gentleman asked is, what were the stability issues with Hdfs? So I guess what I was trying to say is that you might have, well, there are two things. One is the stability issue just with Hdfs, right? The file system is pretty solid for the most part. But we have seen instances where somebody added a bad node into the file system, and while that node was still active, while the data node was still active, writing any data to it would take forever. So what would happen in that case is we would get a lot of sync errors from the Hdfs bolt. I think those were the stability issues I was talking about. Did I answer your question? Okay. Yeah, so we had that, and as soon as we removed that bolt, our topology was running fine. Some of these topologies have been running for months without any issues. I was surprised myself to see a real-time data processing system process that without any errors. When it has errors, it sort of heals itself in the sense that the Kafka spout and the Storm HDFS bold actually use the fail API within Storm. What I'm trying to say that if Storm were to process a message and it can't process it correctly, it would raise an error saying that I can't process it correctly. And then it's the responsibility of what spout you use to do something with that message. You know, that spout may say, hey, I want to throw away this message if I can't process it correctly, or I want to replay this message into the topology. So, yeah. Any other questions? Sure. Yeah, it's a good question. So why choose Storm instead of Spark? I don't know much about Spark to answer that question in a really good way, honestly. When we started this about a year, about a year ago, you know, we weren't sure if Storm Spark was. We didn't know a whole lot about Spark, and although we had seen a lot of buzz about Spark, we had not seen a lot of people running production pipelines within Spark. I may be wrong. I know at this time it's obviously changed from what I hear, and things are building up. But you know, I'm definitely open. You know, if you want to have a conversation after and you think Spark is better, I would love to hear why. Oh, you were just asking. Okay. Yeah. 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 Taylor. Mm-hmm. 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 Yes. Okay. Mm-hmm. Oh, I see. Okay. Okay. There you go. That's a good solution. Great. I don't know if anybody caught that, but what Taylor was saying that there is a solution to the problem I noticed earlier, which is if you were to kill a topology, it uses kill -9 to kill it. And what I was saying, which is fixed in the new version, is that it's not the case. You can ask it to wait until the file gets rotated. That's smart. Any other questions? Sure. Yeah, so with the HDFS part, at least we wanted to make sure that we're not doing crazy amounts of syncs all the time. If we're doing 50 syncs every second, then that's a problem. So we look at the throughput of the incoming data, or a general idea of the throughput. You know, hopefully we're not looking at something which processes one message a second a day for a week, and then the next week it's doing 1,000,000 messages a day, and then the next week it's doing one again. We didn't run into that issue. But if you have a general throughput idea, you can then sort of back calculate and see how often you want your syncs to happen. So we were running about 8 million messages a day, and we were syncing 3,000 messages. That comes to about 30 seconds, a sync once every 30 seconds. And then within the tuning of the topology, there's a whole bunch of internal things within Storm that you can tune, because Storm uses queues within itself to tune it. But that's something that you would want to do if you're getting a lot of data and you just want to maximize the hell out of it. So the question is, what about tuning the number of partitions? I have not looked much into that. We use 7 partitions for a Kafka topic, and we just, yeah. So I have not looked much into that. Yeah. Any other questions? Sure, Taylor. So those of you who didn't hear that, there's a Birds of a Feather session at what time? At 6. So yeah. So more about this, that man is the expert. You can ask him. Cool. If there are no more questions, I will end and stop talking. Thank you very much.